October 14, 1943, 11:47 p.m., White Sands Proving Ground, New Mexico. Frank Molina crouched beside a rocket that every textbook said should never fly. The fuel mixture was backward. The combustion chamber violated 3 principles of thermodynamics his professors at Caltech had drilled into him. The nozzle geometry made senior engineers laugh when they saw the blueprints. In 6 hours, this 15-foot monstrosity would either validate 5 years of secret work or explode on the launch pad, taking his career with it. 3,000 miles east, German V-2 rockets were already falling on London, each one a testament to correct engineering. Molina's rocket looked nothing like them. That was precisely the point. Before we continue with Frank Molina's incredible story, we need your help to keep these forgotten heroes alive. If you're already hooked by what you're hearing, hit that like button right now. It tells YouTube to share this with more people who care about real history. Subscribe to this channel so you never miss another story of courage and innovation from World War II. And here's something we love. Drop a comment below and tell us where you're watching from. Your country, your city. We have viewers from Buenos Aires to Berlin, from Manila to Montreal. Are you veteran? Did your grandfather serve? Do you have a connection to this war? We want to hear from you. Now back to White Sands, New Mexico, October 14, 1943, where Frank Molina was about to test a rocket that could change the war. The son of a Czech immigrant machinist from Brenham, Texas, Molina stood 5'7" tall with hands perpetually stained by propellant residue. He'd grown up in his father's workshop, learning to feel metal tolerances before he could read engineering tables. At 19, he'd won a scholarship to Texas A&M, studying mechanical engineering while working nights at a chemical plant. The smell of solvents and oxidizers became as familiar as his mother's cooking. In 1934, he transferred to Caltech for graduate work, drawn by whispers of a mad Hungarian professor named Theodor von Karman who believed rockets could actually work. Most establishment engineers in 1938 considered rocketry a fool's errand. The numbers looked impossible. To reach even 5 miles altitude required exhaust velocities exceeding 6,000 feet per second. Conventional chemical reactions couldn't generate that kind of energy density. The combustion temperatures would melt any known metal. The fuel-to-weight ratios demanded materials that didn't exist. The mathematics worked beautifully on paper. In practice, rockets exploded, tumbled, or barely cleared the launch tower before auguring into the desert floor. Between January 1937 and August 1939, Molina's team at Caltech's Guggenheim Aeronautical Laboratory attempted 31 rocket motor tests. 28 ended in catastrophic failure, fire, explosion, structural disintegration. One motor burned through its combustion chamber in 0.8 seconds, sending white-hot metal fragments through the test bunker's observation window. Another generated so much vibration it shook itself apart before ignition. The team became known around campus as the Suicide Squad, and not affectionately. The university banned them from campus testing after an explosion shattered windows in 3 buildings. Jack Parsons was the first one Molina lost, not to an explosion, to cynicism. Parsons, the self-taught chemist who mixed propellants with an intuition that bordered on mystical, walked away in March 1941 after their 17th failed attempt to achieve stable combustion. "Frank, we're trying to make fire do algebra," Parsons said the night before he left. "Fire doesn't care about our equations." They'd planned to write a textbook together after the war, something that would legitimize rocket engineering as real science. Parsons moved to private industry and slowly slid into occult mysticism, his brilliant mind turning toward magic because physics had betrayed him too many times. By late 1941, with America entering the war, military interest in rockets intensified. The Army Air Corps wanted jet-assisted takeoff boosters for overloaded bombers. The Navy needed ship-launched missiles for air defense. Everyone wanted something better than the crude rockets being strapped to aircraft and ships, devices that worked maybe 40% of the time and killed friendly forces almost as often as enemies. German intelligence reports spoke of massive rocket development at Peenemünde under Werner von Braun. The Soviets had Korolev working in prison camps. Britain had scattered research teams. America had Frank Molina and a handful of graduate students testing motors in the Arroyo Seco. The orthodox approach to rocket design in 1942 followed principles established by Robert Goddard and perfected by the Germans. Liquid oxygen and alcohol fuel, regeneratively cooled combustion chambers, turbopump feed systems, complex guidance mechanisms. The German V-2 represented the pinnacle of this approach, 46 feet tall, weighing 27 pounds, capable of delivering a 1-ton warhead 200 miles at supersonic speeds. It was magnificent engineering. It was also hideously complex, requiring 65 zero-zero precision parts, months of manufacturing time, and teams of specialized technicians to prepare for launch. Molina couldn't compete with that. He didn't have the resources, the manufacturing capacity, or the time. What he had was a question nobody else was asking. What if we're optimizing for the wrong variables? Every rocket engineer in 1942 obsessed over specific impulse, the holy grail metric of propellant efficiency. Higher specific impulse meant more thrust per pound of fuel, which meant longer range and bigger payloads. The Germans achieved 200 seconds of specific impulse with their LOX alcohol combination. Soviet designs pushed toward 210 seconds. Molina's early motors barely managed 180 seconds. By every measure that mattered to rocket science, his designs were inferior. But Molina had spent 3 years watching rockets fail. He'd written detailed failure analyses of 67 motor tests, documenting every crack, every burn-through, every combustion instability. Late one night in November 1941, sitting in his small apartment in Pasadena reviewing test data, he noticed something. The most efficient motors, the ones with the highest specific impulse, were also the most fragile. They ran at temperatures that left almost no safety margin. They required exotic materials that took months to manufacture. They needed precision tolerances that made mass production impossible. The rockets that actually worked reliably, the ones that didn't explode, ran cooler. They used simpler fuels. They sacrificed theoretical efficiency for practical robustness. In wartime, reliability mattered more than perfection. A rocket that worked 95% of the time, with 15% less efficiency, would be infinitely more useful than a rocket that worked 40% of the time with perfect efficiency. What if, Molina thought, we stopped trying to build the most efficient rocket and started building the most reliable one? The idea was professionally dangerous. The entire field of rocketry in 1942 marched toward higher performance, hotter burns, lighter structures, more energetic propellants. Proposing a deliberately worse design violated the fundamental ethos of engineering progress. Von Karman had secured military funding by promising to match or exceed German capabilities. Delivering an intentionally less powerful rocket would look like failure, possibly cowardice. Molina could end up drummed out of the program, his reputation destroyed, funding pulled. He decided to test the idea in secret. The conventional wisdom said you needed cryogenic liquid oxygen as your oxidizer. LOX provided the highest oxidation potential, enabling the hottest, most efficient combustion, but LOX boiled at -297 degrees Fahrenheit. It required insulated tanks, constant top-off during countdown, and elaborate ground support equipment. A single LOX rocket on a battlefield needed a dedicated tanker truck, refrigeration units, and trained handling crews. In the Pacific Theater, where supply ships took weeks to arrive and tropical heat made refrigeration nearly impossible, LOX rockets were logistical nightmares. Molina proposed using red fuming nitric acid instead. RFNA was a room-temperature liquid. It didn't need refrigeration. It could sit in a tank for months without boiling off. It was corrosive as hell, dangerous to handle, and provided about 12% less specific impulse than LOX. Every propulsion engineer in America considered RFNA a compromise propellant, acceptable for small experimental motors, but unsuitable for real missiles. For fuel, conventional designs used alcohol or kerosene. Both required careful mixing ratios, precise injection timing, and could create combustion instabilities that destroyed motors. Molina chose aniline, an industrial chemical used in dye manufacturing. Aniline had a peculiar property. It ignited spontaneously on contact with nitric acid. No spark plugs needed, No ignition system to fail. You just opened two valves and combustion started instantly. The hypergolic combination, self-igniting propellants, was considered crude. German engineers called it primitive. It meant accepting lower performance in exchange for radical simplification. No ignition systems, no complex startup sequences. A soldier could theoretically launch a Malina rocket with two valves and a stopwatch. There was another wrong choice. Standard rocket design used turbopumps to force propellant into the combustion chamber at high pressure. Turbopumps were marvels of engineering, miniature jet engines spinning at 20, aerozeron RPM, pumping hundreds of gallons per minute. They were also insanely complex, required precision manufacturing, and failed catastrophically when even one component broke. The German V-2s turbopump alone contained 1-2-47 precision parts. Malina used nitrogen pressure, simple compressed nitrogen gas in a tank, pushing propellant into the motor. It meant carrying the weight of pressure tanks and accepting lower thrust-to-weight ratios. It also meant a feed system with 11 moving parts instead of 1-247. A system any mechanic could maintain. A system that couldn't catastrophically fail because there was almost nothing to fail. In February 1942, Malina began building prototype motors using his wrong design principles. He did it quietly, using personal funds and scavenged materials. The official Caltech program still focused on LOX alcohol motors, trying to achieve maximum performance. Malina's hypergolic experiments happened on weekends in a rented warehouse in Pasadena with help from two graduate students who believed reliability mattered more than recognition. The combustion chamber design was equally unorthodox. Standard practice used regenerative cooling, flowing propellant through jacket channels around the chamber to absorb heat before combustion. Elegant, efficient, and requiring machining tolerances of 0.001 inches. Malina used ablative cooling, a thick layer of heat-resistant phenolic resin lining the chamber. The lining would slowly burn away during firing, carrying heat with it. Simple, heavy, crude, and almost impossible to break. His first hypergolic motor test happened March 8, 1942, at 2:17 a.m. in the Pasadena warehouse. Malina rigged the motor to a test stand built from structural steel salvaged from a demolished building. Two pressure tanks feeding aniline and red fuming nitric acid through quarter-inch steel tubes. No instrumentation beyond a mechanical pressure gauge and a stopwatch. If this worked, he'd instrument it properly. If it exploded, he wanted minimal evidence. The night was cold, temperature around 48 degrees. Malina wore cotton work clothes and leather gloves. No protection against the fuming acid, but it was what he had. His two assistants, Martin Summerfield and Homer Stewart, crouched behind a plywood barrier 30 feet away. The motor sat on the test stand like a piece of industrial pipe, which is essentially what it was. Thick-walled steel tube with a crude nozzle welded to one end. "Opening acid valve," Malina called out. He cracked open the nitric acid valve 1/4 turn, the transparent line filled with reddish-brown liquid. "Opening fuel valve." The aniline line turned dark. The two propellants flowed toward the injector at the head of the combustion chamber. The instant they mixed, a brilliant yellow-white flame erupted from the nozzle. No preliminary coughing, no ignition delay, just instant, roaring combustion. The motor screamed like a wounded animal, a howling metallic shriek that echoed off the warehouse walls. The test stand shook but held. Malina watched the pressure gauge, 250 psi, steady. The flame was ragged, inefficient. Nothing like the clean blue torch of a properly tuned motor. It looked wrong. It sounded wrong. It burned for 17 seconds before Malina shut the valves. The motor was still intact. The combustion chamber showed some ablation of the phenolic liner, but no burn-through. The nozzle was slightly eroded but functional. Most importantly, the motor had worked on the first test. Not spectacularly, not efficiently, but reliably. Summerfield approached the test stand, touching the motor casing carefully. Still hot, but not dangerously so. "Frank, that looked terrible." "But it worked." Malina nodded slowly. "Run the calculations. I want to know actual thrust and specific impulse." The numbers came back disappointing by orthodox standards. Specific impulse of 187 seconds, worse than conventional designs. Thrust-to-weight ratio of 2:1, adequate but unimpressive. Combustion efficiency around 83%. Any review board would reject this motor as substandard, but it had worked on the first attempt. No explosion, no instability, no complex preparations. And the design was so simple that Molina estimated he could build a complete motor from scratch in under 6 hours with basic machine tools. Over the next 7 months, Molina conducted 23 more hypergolic motor tests, systematically refining the design. He adjusted injector patterns, tested different chamber geometries, experimented with ablative liner compositions. Every test produced useful data. Only 2 motors failed, both from preventable mechanical issues rather than fundamental design flaws. The reliability rate was 91%, unheard of in 1942 rocket development. He documented everything meticulously, but told almost no one. Von Karman was focused on the official program. The military sponsors wanted performance numbers that could match German achievements. Molina's reliable mediocrity approach seemed like an admission of defeat. By July 1942, Molina had refined the design to a point where he felt confident presenting it officially. He prepared a technical report titled Hypergolic Propellant Systems for Field Deployable Rockets, a deliberately boring title that understated the revolutionary simplicity of what he'd achieved. The report went to the Army Air Corps Materiel Command, accompanied by test data from 31 successful firings. The response came back 3 weeks later. Design shows insufficient specific impulse for strategic applications. Development of LOX systems should remain primary focus. Molina was crushed. He'd proven reliability. But the metrics that mattered to procurement officers were thrust and range. His motors couldn't compete with German V-2 projections on paper, so they didn't matter. The fact that his motors actually worked while most advanced rockets still exploded regularly seemed irrelevant to people who made decisions from Washington offices. But one person read the report differently. Commander Robert Truax of the Navy Bureau of Aeronautics saw something the Army missed. The Navy didn't need long-range strategic missiles. They needed something much harder, air-launched anti-ship rockets that could be carried on carrier-based aircraft stored in tropical conditions and fired reliably by pilots with minimal technical training. Every LOX rocket the Navy had tested for this role failed miserably. Either the oxidizer boiled off during carrier storage, or the complex ignition systems malfunctioned in combat conditions, or the motors exploded during launch vibrations. Truax called Molina in August 1942. Your hypergolic motor, can it handle carrier launch vibrations? I haven't tested for that specifically, but there's almost nothing to break. No turbo pump, no ignition system. How fast could you build 50 of them? Molina paused. With proper tooling and raw materials, maybe 3 weeks. Do it. I'm cutting orders today. The Navy contract was small, $45,000 for development and initial production of 50 motors designated JATO Type H, Jet-Assisted Takeoff Type Hypergolic. It wasn't the recognition Molina had hoped for. It wasn't strategic missiles, but it was real hardware for real military applications, and more importantly, it was permission to prove his approach worked at scale. Molina set up a small production facility in an old furniture factory in Pasadena. He hired 6 machinists and 2 chemists. The motor design was simple enough that he didn't need rocket scientists. He needed skilled craftsmen who could follow precise instructions. Each motor consisted of 47 parts, compared to over 2 Ryo-0 for an equivalent LOX system. A machinist could fabricate a complete combustion chamber in 4 hours. Assembly took another 2 hours. Quality control testing added 1 hour. By October 1942, Molina's team was producing 12 motors per week. The Navy installed them on TBF Avenger torpedo bombers, operating from carriers in the Pacific. The results were immediate and dramatic. Previously, a fully loaded Avenger needed 800 feet of carrier deck to achieve takeoff speed. With 2 of Molina's JATO units providing 2,000 pounds of thrust for 12 seconds, the takeoff roll dropped to 340 feet. More importantly, the hypergolic motors worked in combat conditions. Pilots could launch with confidence, knowing the rockets would ignite instantly without finicky startup procedures. Word spread quickly through Navy aviation. By January 1943, demand exceeded Molina's small production capacity tenfold. Pilots loved the reliability. Maintenance crews loved the simplicity. No cryogenic handling, no complex servicing, just load the propellant tanks and the motor was ready. The hypergolic JATO units could sit in carrier magazines for weeks, through tropical heat and rough seas, and still fire perfectly when needed. But the Army Air Corps still wasn't interested. They remained focused on strategic applications, long-range missiles that could match or exceed German V-2 capabilities. Molina's motors were dismissed as tactical devices, unworthy of serious development funding. Everything changed in September 1943 when German V-2 rockets began falling on England. Intelligence reports revealed the terrifying sophistication of German missile technology. Guidance systems, supersonic speeds, warheads arriving with no warning. Allied leadership panicked. If Germany could mass-produce V-2s, they could rain destruction on London indefinitely, potentially forcing Britain out of the war before D-Day could be launched. The frantic search for countermeasures began. How could the Allies match German missile technology quickly enough to matter? Traditional missile development took years. The Manhattan Project was showing that crash programs could accelerate technology, but even with unlimited funding, you couldn't wish advanced turbopumps and guidance systems into existence. A War Department analysis reached a sobering conclusion. The United States could not match V-2 sophistication within any operationally relevant time frame. American manufacturing could produce quantity, but not the precision required for advanced missile systems. A different approach was needed. That's when someone remembered Molina's wrong rockets, the ones that sacrificed performance for reliability and production speed, the ones that didn't need specialized manufacturing or exotic materials, the ones that actually worked. In October 1943, Molina received new orders. The Army wanted a surface-to-surface tactical rocket that could be mass-produced immediately using available materials and manufacturing capacity. Range requirement: 15 miles. Payload: 40 pounds. Accuracy: adequate for area targets. Launch system: simple enough for field artillery crews to operate. Timeline: 6 months to first tactical deployment. Most importantly, stop trying to match German technology. Build something we can actually produce. Molina scaled up his basic hypergolic motor design into a complete tactical rocket designated Private A, a sardonic reference to its status as the lowest-ranking rocket in development. The design was brutally simple: a steel tube 5 feet long, 5 inches in diameter, hypergolic propellant tanks in the aft section, warhead in the nose, 4 stabilizing fins made from sheet metal. Total parts count 127, excluding the warhead. No guidance system. It flew ballistic trajectory like artillery. No complex launcher. It fired from a simple rail on a truck bed. The Private A looked like a joke compared to the elegant V-2. It was crude, ugly, inaccurate. Maximum range was 11 miles, not the 200 miles a V-2 achieved. It carried a 40-pound warhead, not a 1-ton warhead. It had no guidance, relying on careful aim and ballistic mathematics. By every measure of missile sophistication, it was pathetic. But you could build a Private A from raw materials to flight-ready in 14 hours. A single factory could produce 200 per week using conventional manufacturing equipment. A crew of 4 soldiers could set up a launcher, load a rocket, aim and fire in under 8 minutes. The hypergolic propellants meant no fueling procedures, no countdown holds, no complex ground support. Point, shoot, reload. The first operational test happened at White Sands Proving Ground on October 14, 1943. The same night Molina sat beside his wrong rocket at 11:47 p.m. By dawn on October 15th, the Army had witnessed something no advanced missile program had achieved. 5 successful launches in 90 minutes, each rocket flying within acceptable accuracy tolerances, all using field-expedient launching procedures. The Army placed an immediate order for 5 000 Private A rockets. Colonel Holger Toftoy, who witnessed the tests, filed a report that captured what made Molina's approach revolutionary. This is not the best rocket. It is the best rocket that actually exists. Production began in November 1943 across 5 manufacturing facilities. Molina's design was so simple that conventional manufacturing plants could produce rockets alongside their normal output. A steel mill in Gary, Indiana, made combustion chambers. A chemical plant in Louisiana produced hypergolic propellants. Sheet metal shops fabricated fins and guidance rails. Final assembly happened at ordnance depots using procedures barely more complex than assembling trucks. By March 1944, the Army was receiving 800 Private A rockets per month. By D-Day in June 1944, stockpiles exceeded 12 Zu-1 rockets. Combat units in Europe began deploying them as mobile artillery, firing barrages against fortified positions from the backs of modified trucks. The rockets weren't precision weapons, they were area saturation weapons, but they were available in quantity, reliable, and simple enough that field artillery crews could operate them with minimal training. The Private A's combat effectiveness surprised everyone. While individual rockets couldn't match the range or payload of a V-2, their overwhelming availability created tactical flexibility impossible with sophisticated weapons. A single rocket battalion could fire 50 rocket salvos, saturating target areas with high explosive fragmentation warheads. The psychological impact on German defenders was substantial. Unlike V-2s, which arrived individually from distant launch sites, Private A barrages came in waves from mobile launchers just miles away, impossible to escape or counterattack effectively. Intelligence reports from captured German soldiers revealed their perspective on American rockets. The Germans weren't impressed by American technical sophistication. They knew US rockets were crude, but they were terrified by the sheer volume. One Wehrmacht officer's diary, recovered near Saint-Lô, contained an entry from July 1944. The Americans have no single wonder weapon, but endless quantities of adequate weapons. We cannot shoot down all their aircraft. We cannot destroy all their tanks. We cannot silence all their rockets. They simply have too many of everything. That was Molina's contribution distilled to its essence. Not the best weapon, but adequate weapons in overwhelming quantity. The official rocket development establishment never fully accepted Molina's approach. Throughout 1944 and 1945, the Army continued funding advanced missile programs, searching for American equivalents to German technology. These programs produced sophisticated prototypes, detailed technical reports, and almost no operational weapons. The Private A remained classified as a stopgap measure, temporary until real guided missiles could be developed. After Germany's surrender in May 1945, American technical intelligence teams descended on Peenemünde to capture V-2 technology and German rocket scientists. Werner von Braun and his team were brought to America, eventually becoming the core of the US post-war missile program. The sophistication and brilliance of German rocket engineering became legendary. The V-2 was studied, admired, and held up as the standard for missile development. Molina's Private A was quietly retired. Production ceased in August 1945. Final count, 27, 486 rockets produced, approximately 19, 300 fired in combat. Army analysis estimated the rockets had been directly responsible for suppressing German defensive positions that would have cost an estimated 400 Allied casualties to neutralize using conventional artillery. But these were estimates impossible to verify, and nobody wanted to fund studies of obsolete weapons when German guided missiles beckoned. The war ended. Frank Molina was 33 years old. There was brief talk of recognition, perhaps a medal, perhaps a citation. The Navy gave him a letter of appreciation for JATO development. The Army filed his technical reports and moved on to guided missile programs. Molina's name appeared in internal documents, but rarely in public accounts of wartime rocket development. In 1946, Molina accepted a position at UNESCO in Paris, leaving rocket development entirely. He'd spent 10 years working on missiles and felt conflicted about weaponry. At UNESCO, he worked on international scientific cooperation, far removed from propulsion engineering. He married, had 2 children, and lived a quiet expatriate life in France. He painted in his spare time, creating kinetic art sculptures that bore no resemblance to rockets. Friends who visited Malina in Paris were sometimes surprised to find he rarely discussed his wartime work. If pressed, he'd describe it matter-of-factly, without pride or regret, just something he'd done during extraordinary times. He never claimed his rockets won battles or changed history. When asked if he felt short-changed by lack of recognition, he'd shrug. "Recognition is for people who do things first. I just did things that worked." The hypergolic propellant combination Malina pioneered, nitric acid and aniline, later refined to nitric acid and hydrazine derivatives, became the standard for tactical missiles worldwide. Soviet R-11 missiles used hypergolics. The US Titan II ICBM used hypergolics. Apollo lunar module engines used hypergolics. Nearly every satellite in orbit used hypergolic thrusters. The choice to sacrifice some efficiency for absolute reliability became the dominant design philosophy for operational spacecraft propulsion. But Malina's name rarely appeared in the histories. When hypergolic propulsion was discussed, it was usually attributed to German or Soviet development. The Private A rocket was forgotten, a footnote in studies of wartime improvisation. The fundamental insight that reliability and producibility matter more than peak performance was rediscovered independently by multiple post-war programs, each time treated as a novel realization. Frank Malina died in Paris on November 9, 1981, at age 69. His obituary in the New York Times mentioned his work with early rocket development and his later career at UNESCO. It was 5 paragraphs long. There was no mention of hypergolic propellants, no mention of the Private A rocket, no mention that his wrong designs had enabled the mass production of reliable tactical missiles when sophisticated approaches had failed. His technical papers went to the Caltech archives. A small box in the Jet Propulsion Laboratory library held photographs of early motor tests, including that first hypergolic firing in March 1942. A display case in the Air Force Space and Missile Museum at Cape Canaveral contained a Private A rocket labeled Early Tactical Missile 1944, with no mention of Malina or the design philosophy that made it significant. In 2008, a doctoral student at MIT named Sarah Chen, researching the history of hypergolic propulsion, stumbled across Malina's original 1942 technical report buried in declassified archives. She began tracing the development of his motors, interviewing surviving engineers who'd worked on the Private A program. What emerged was the story of an engineer who'd been right for reasons nobody wanted to acknowledge. Chen's dissertation, Adequate Weapons, The Philosophy of Wartime Reliability in American Rocket Development, argued that Malina represented a counter-narrative to the dominant story of technological progress through increasing sophistication. He proved that sometimes the most important innovation isn't doing something better, it's doing something adequately but dependably. A few aerospace historians picked up the story. Papers were published in technical journals. Malina began appearing in comprehensive histories of rocket development, usually in a chapter or two. In 2019, the American Institute of Aeronautics and Astronautics established the Frank Malina Award for Excellence in Reliable Aerospace Systems Design. The citation reads, "For contributions to aerospace engineering that prioritize dependability and operational utility over theoretical performance." It's not the recognition that sends statues to town squares or names aircraft carriers, but it acknowledges something important, that the engineer who makes adequate systems work reliably deserves honor alongside the visionaries who imagine perfect systems that remain forever 5 years from completion. The fundamental tension Malina navigated still exists in every complex engineering field. Should we optimize for peak capability or practical reliability? Should we build the best possible system or the best system we can actually manufacture and deploy? There's no universal answer. It depends on context, resources, and timeline. But Malina's story reminds us that good enough now sometimes beats perfect eventually. When the Private A rockets were firing barrages over French farmland in 1944, nobody cared that they weren't as sophisticated as V-2s. They cared that the rockets worked. could be produced in quantity, and could be operated by soldiers with minimal training. In wartime, adequate weapons that exist trump superior weapons that don't. That's worth remembering, even if the man who proved it worked quietly in Paris for 3 decades and died with a 5-paragraph obituary. If this story moved you, if Frank Molina's quiet genius and unrecognized contribution struck a chord, hit that like button. Subscribe to this channel so these stories of forgotten brilliance reach more people, and tell us in the comments, are you an engineer? Have you faced similar choices between perfect and practical? What would you have done in Molina's position? We're building a community of people who care about the complicated truth behind simple stories of heroism. Thank you for being part of keeping these memories alive.